Integration by parts is a huge tool in your arsenal to solve integrals by hand. And let me start with this. Let u of x and v of x be differentiable. Then the derivative with respect to x of their product is well known to you by now. Well, you know it as the product rule. We get u prime of x times v of x plus u of x times v prime of x. Next, let me go ahead and undo what I just did by taking the integral of both sides with respect to x. So the way that's accomplished now, as it stands right now, you're probably like, what in the world is this even doing here? This looks like nothing we've ever done. Oh, give me a minute here. This side over here, I'm going to break this up into the integral of u prime of x v of x dx plus the integral of u of x v prime of x dx. On the right-hand side, sorry, the left-hand side, let me fix this for a minute. I put a dx there for a reason. All right, now a little aside I have to tell you is that what happens here and what happens here is important. I'll tell you what I'm talking about. You probably remember the differential with respect to y was equal to dy over dx times delta x. But delta x happens to be dx because that's the variable, the independent variable. So it very well does look like you could cancel out the x's. So if you keep that in mind, look right here. This certainly looks like I could cancel out those x's. I don't want to be too glib about that. There's a lot of work that was done into making the limits all work out and making this notation all happen to work out so it looks like you're actually doing division. Technically speaking, limits are things that are working in the background. But here, right here, another version of this is that delta f, if f is a function of x, is f prime of x times delta x, or just as before, that's dx. All right, so what I have here then is the integral. I'm going to drop the of x's because the notation is usually not given in terms of x. But the leftmost integral changes to this. So I don't have u of x, v of x. Over here, right here, this guy combined with this guy here is du. Similarly, this guy here is dv. So it's going to act that way. You're going to act like your u is your variable, or that v is the variable. You'll see how it works as we do some examples. So this changes to the integral of v du plus the integral of u dv. Now what happens is an integral undoes the differential. So maybe to remind you, the integral of dy equals y plus c. The integral of dz equals z plus c. I mean, you get the idea. I don't know how many more I should do. One more. The integral of d smiley face equals a smiley face plus c. So whatever is after the d is what the answer is going to be. So right here, the answer will be uv. Now I'll put a plus c when I'm done with these integrals here. Now the way that this is typically given is not that form. What's typically done is we subtract this integral from both sides, and we get uv minus the integral of v du equals the integral of u dv. Of course, they never give it in that order. They actually put this on the left-hand side, so we'll go ahead and do it. This is the integration by parts formula. So it goes like this. U dv equals uv minus the integral of v du. And there's the formula that is always referenced in textbooks. For my first example, I want to show the probably the starter example for everybody for this particular kind of problem. We'll just do the integral of x e to the x dx. Now your task is to identify a u and a dv in the integral, and then use those u's and v's and whatever else to solve this. Conceivably, this integral will be easier than this one. So this is the bad integral. We want to make it easier by doing this stuff. Now, it doesn't look easier, but by easier, I mean actually something we can actually get an integral for. So I'll start us off here. In this one, it really wouldn't have mattered. I think I'm going to let u be that, and then this will be dv. So the way the book writes it up, most books nowadays, they switched it on me from when I did this stuff. So I'm going to do it the way that I always have, and you have to adapt. Okay, so if I let u equal x, then the derivative of x is 1, but then don't forget to put dx, just like you've always done with integrals. So the dv is going to have, dv is the one that has the dx already attached to it, e to the x dx. And if you take the antiderivative, that's what you got to do. To go from dv back to v, you've got to take the antiderivative of this. The antiderivative of e to the x is e to the x. You do not have to put a plus c just yet, because you're still in the middle of the problem. When I'm done with the problem, I'll just put a plus c. And it really, there was no restriction on v here anyways. You can find any v you want so long as it works. So anyways, let's follow this. That equals, so accordingly then, I have to do uv, well let me write that, uv minus the integral of v du, and then I'll write what goes into what slot so you can see it. So where the u is the x, where the v is the e to the x, minus the integral. Now where is v? V is e to the x. And du, where to go, was just dx. So you can see I have part of my answer, but then this here is an easy integral to do. The integral of e to the x is simply e to the x. So you get x e to the x minus e to the x plus c. An important note about this problem is the following. Why did I choose this and this? Well, because I wanted the x, if I take the derivative of x, it turns to 1. It's always easier to work with a 1 than it is with an x. Had I put an e to the x here and taken the derivative, it still would have been e to the x, which is not necessarily a bad thing, but then I would have been stuck with x dx over here, And then when I took the antiderivative, I would have had x squared over 2, which would have been a worse integral than the beginning one. So switching that order would not have been good. Sometimes you can get away with switching the order. It's not always one way, and that's the only way to do them. For the next example, I'll try to explain my motivations a little better this time. We're going to do the integral of the natural logarithm of x dx. This is another common one that's always given. Now you have to try to identify a u and a du in here. There's not a lot. You can let this be u, and then this be du, I guess. I guess technically you could let u equal 1, but that would never be worthwhile because then its derivative is 0. It wipes out the problem. So u is ln of x, du could be just dx, or 1 times dx. Let's try that. The derivative then is 1 over x, and don't forget to attach the differential of x, dx. These are here to help you keep lined up in what you're doing, what needs to have an integral and things like that. And then I have dv was dx. Okay, let me write those down so you know what I'm using. There's u, there's dv. Antiderivative of dx is simply x. And now I'll go ahead and apply my formula. We have uv, so I have x ln x. I think it looks better if the x comes first. If you switch it, it gets confusing, I think. And then I'm supposed to do minus the integral of v x du. See what it does here? Now I've done these in advance. So I'm not probably going to scramble around on these like you would and do trial and error. And I don't think it is very helpful for me to stumble through a lot of these problems either. Trial and error is something where you'll learn better by tackling them than watching me do them anyway. So I think the best thing I can do is just provide a very a paradigm for how to do these problems, and then maybe you can follow my lead. So right here then, I just have the integral of dx, which is an extremely easy integral to do. It simply equals x. Now if you want to, obviously, if you take the derivative of the answer, you should go back and get the original ln of x dx. I'll move on to example 3. Now you might allow u to equal sine, but then its derivative is cosine, and that doesn't really make the problem easier. I think if you let u equal x, then at least its derivative is 1, which is an easier thing to work with than x. So I think in this case, just like before, I'm going to let u equal that, and then this stuff will be du. So u will equal x, du equals 1 dx. So this has a nice chance of making the problem easier, because dealing with 1 is always easier than dealing with a variable. Then dv is that sine of 2x dx. Now, to get this, you actually need to do a little mini U substitution. Okay, let w equal 2x. Then dw equals 2 dx. And that means that w over 2 would equal dx. So in any case, I'm going to get 1/2 cosine of 2x. Well, let's see what we end up with here. So uv will be x times 1/2 cosine of 2x minus the integral, and this I need to do a v du v. I'll put the 1/2 out here. Du is just dx. And this will satisfy the same thing as before. If you let a w say equal 2x, then dw equals 2dx, divide by 2 to get 1/2 w, and then what will happen is this will become a 1/4. And so you get the 1/4 sine of 2x, like I said. I made a mistake in this problem right here. If I take the antiderivative of sine, I do get the 1/2, but it should be negative 1/2. So I'll put that there. That means this piece will become a positive, and that will become a positive. This next one is nearly identical to the previous one, except it doesn't look as easy. But here, I would definitely want to use u equals theta, because then du would be 1 d theta. But better than that, I do want to take the integral of this stuff, because the antiderivative of secant squared is tangent. So that will have a nice integral that's doable. Many times you want to choose your dv to be an integral that is at least doable. So let's let u equal theta, and then du will equal d theta. I'm going to drop putting that 1 in there. dv will equal secant squared theta d theta, and then v equals tangent of theta. So this equals uv, so I get theta tangent of theta minus v du. V is tangent of theta. And then du is no different than d theta. Now, you may or may not have ever done this particular integral in your first calculus class. So the way that you would do it is this. I'm going to leave this stuff here, but I'm going to call this sine of theta all over cosine of theta d theta. Okay, so now I'm not going to use u and v because I used them before. I'll use w as my substitution, will be cosine of theta. Then dw equals negative sine theta. So right here, if you look, there's my w down here, and negative sine theta d theta is my dw. So what that means is that I have 1 over w, positive 1 over w. Then it shouldn't surprise you when I write this, because the antiderivative of 1 over the variable is the natural log of the absolute value of that variable. So you can check those details on your own. For the next example, this is sort of like the natural logarithm one, because when I give it to you, you don't have a lot of choices here. To let u, what would u equal? Well, u that only has one choice, sine inverse of x. It really does. So the du has to be the dv has to be dx. So I'll put my u. That's arc sine of x. du equals 1 over the square root of 1 minus x squared dx. And right now, this looks bad, but you didn't have a choice. Remember, u can't be this part. U is not a differential. So this has to be dv. The antiderivative of dx is simply x. So this equals uv will be arc sine of x times x, but I'll write it as x times arc sine of x, so as not to be so confusing. Now this ends up not being nearly as bad as you may think. My v is x, my du is the square root of 1 minus x squared dx. And now this is not a bad problem at all, because if I let w, say, equal this stuff, I almost get that. So I'll do w equals 1 minus x squared dw equals negative 2x dx. See, I have the negative x. Let me do it this way. I have the negative x dx where I want it. So I'll divide by 2 to get 1/2. So we end up with x arc sine of x plus 1/2. I'll have 1/2 dw will be all that stuff. Down here will be the square root of w. So I'm going to write it as w to the negative 1/2 dw. That is way more appealing than having the square root to work with. So I get x arc sine of x plus 1/2. If I take the antiderivative of this, I'll get w to the 1/2 over 1/2, which will actually be 2. And then I'll replace w to the 1/2. Then I'll replace w with 1 minus x squared. We get x arc sine of x plus, I guess for display purposes, the square root sign I guess isn't so bad. Everybody seems to like that one. Alright, when choosing my u's and v's, my first most obvious choice is perhaps u would be x squared. But when I take the derivative, then that's 2x. That's a little bit easier. But then if this is my dv, I've got to try to integrate ln of x squared, and I don't know how to do that. So if that were my choice, I wouldn't do that. So you're kind of stuck, if you want to have at least a shot at starting somewhere, is I could let u equal all of ln of x squared. And then du would equal, bring the 2 down, then multiply by the derivative of the inside via the chain rule, 1 over x dx. And then dv is x squared dx. And you can see here, at least I can integrate this thing. I don't know if that makes it better or not, but at least I can integrate it and get somewhere. And at least I could differentiate this thing and get somewhere. So anyways, this integral becomes uv, so I'll have 1/3 x cubed times the natural log of x squared minus, and then we're going to have v du. So let me go ahead and put all that together. My v is 1/3 x cubed, and then my du is 2 ln of x times 1 over x dx. So at least I've got this going on. I'll bring the numbers out front. Let's see what we have. So I'll have x squared ln of x dx. Okay, well at least I've taken a 2 out of there, so this is seemingly a little bit better. Now this time I'm going to do it again. This is a multiple application of integration by parts. If I let u equal ln of x, just ln of x this time, when I take its derivative, I'll get 1 over x, which is great because the thing I have to integrate in the end is that v du, and the v will be like 1/3 x cubed, and the du will simply be 1 over x. So the x's will cancel. It'll look very nice. So I'm going to do it again. Second application of integration by parts again. I will not use different letters. Let's say the variables are renewed. So this time, I'm not going to let u equal x squared. Oh, I guess I didn't the first time. I let it be the ln stuff. So I'm going to let it equal ln. Because ln kind of brings things down when you take its derivative. It's 1 over x. And if the other thing is just a polynomial in x, then you're going to have some canceling. So I'll have that will be ln of x du will equal 1 over x dx. dv will equal, so that'll be x squared dx. And v then is 1/3 x cubed. So be very careful. Do not try to do this in your head. I've seen too many people try to do it and fail. It's not a big thing. It's just you're going to lose track of all the minuses and things like that. So what I'm talking about is this, minus 2/3. I'm not afraid to put a big bracket and then put my uv inside of here. 1/3 x cubed ln of x minus, it's got its own uv, and v du. 1/3. Notice here then that x to the third and 1 over x will give me an x squared. The whole purpose of this is this minus is going to help me keep track of things and not screw them up. So here then I'm going to have minus 2/9 x cubed ln of x. And I'll have plus, I'm going to bring this 1/3 out, I'll have plus 2/9 the integral of x squared dx. And so all that's left is to do this. Don't forget to put your plus c on the end of it when you're done. I think of it, did I put a plus c on the last one? Yes. So this equals 1/3 x cubed ln squared of x minus 2/9 x cubed ln of x. Now when you take the antiderivative of this, you're going to get x to the third over 3. So I'll get plus 2 over 27 x to the third plus c. There's sort of a rhyme or reason here too. Look at the way these gone. 3, 9, 27, and then the x cubed is there in every one of them, but ln squared, then ln, and then there was none. So it was chipping away at the ln's. This next example features a very robust integral. We have e to the negative 2 theta times sine of 6 theta d theta. Now this is difficult. You can integrate and differentiate either one of these with equal ease, I think. You're going to get some fractions when you take the antiderivative, so it really doesn't matter. The derivative of e to the anything is that e to the same thing. However, because of the chain rule, I have to take the derivative up here, and I'll get negative 2 d theta. And then for dv, I have sine of 6 theta d theta. It's the same kind of a game as before. You're going to get better at integrating if you want to do these in any kind of a reasonable amount of time. If I were to integrate this so that I can go up to v, I would, let's say, w equals 6 theta. Then dw would be 6 d theta. I would divide by 6 to get 1/6 dw. In other words, you'll find you're going to get 1/6 cosine 6 theta. Not just that. Remember, the derivative of v has to be dv. The derivative of cosine is negative sine, so if I'm going to go backwards, I better have a negative here. Alright, so this thing equals uv. I'll put the negative 1/6 in front. E to the negative 2 theta cosine of 6 theta, and then I have to take minus v du. Now notice that this minus and this minus will cancel, but I'll still have the minus from the original minus in the problem. So v then, I'll have 1/6 cosine of 6 theta times, so 2 times 1/6 will be 1/3. Let me put that out front. And then that'll leave me with e to the negative 2 theta times cosine of 6 theta. Now, we're doing repeated applications of this particular formula, the integration by parts. And the problem with both e and both sine and cosine is that you can't differentiate them away. E you can differentiate forever and it's still e to the something. You can differentiate cosine all day long, it becomes sine, then cosine, then sine, then cosine. You'll get nowhere different, but the game we're going to play involves the fact that sine and cosine, the derivative of one is the negative and the other one is not. So that's going to play a role in what we do here. Let me explain what I mean. I'm going to now apply the integration by parts formula to this again. But I want to, since I did this here, I don't want to change it back. If I changed and put, if I changed and made e to the negative 2 theta d theta, and I put that down here, you would simply go back and undo what you did. So if you're going to want to go on and actually do something, do the same thing again. So I'm going to let this part be my u. Then my du is just like before, negative 2 e to the negative 2 theta d theta. My dv will be what's left over, cosine of 6 theta d theta. And as before, the v then will be 1/6 sine 6 theta. This time there is no need for a negative because the derivative of sine is positive cosine. And this turns out to be the key to the whole problem. So let me rewrite as much as I have. I have negative 1/6 e to the negative 2 theta cosine of 6 theta minus the 1/3 in brackets now. My uv, I'll have 1/6 e to the negative 2 theta sine of 6 theta too soon, and then minus vdu. Not sure how that happened. Minus vdu, but since there's a negative here, it'll actually end up being plus. And then I'll have 1/3. I'll have then e to the negative 2 theta sine of 6 theta. Boy, I'm going to have to give myself some more room because I am going to multiply this all through. I'll see if I can somehow figure out a way of writing smaller because I want the other integral in here too, the original one. I want it back. So there it is, e to the negative 2 theta sine of 6 theta. This is what I have so far. So I have negative 1/6 e to the negative 2 theta cosine of 6 theta. Then I'll go ahead and start multiplying through here. So I'll get negative 1/18 e to the negative 2 theta sine of 6 theta. And then I'm going to have to wrap around down here. Then we get minus 1/9 the integral of e to the negative 2 theta sine of 6 theta d theta. Now, as you can see, this here is no different, at least this particular integral right here is no different than the original integral. So it may seem like we've not done anything, but we actually have. Now, I had a 1 over here in front of it. Now I have a negative 1/9. As long as it's different from 1, that doesn't matter to me. I'm going to add this to both sides of the equation. So I'm going to add 1/9, the integral, e to the negative 2 theta, sine of 6 theta d theta, and I'm going to add it to the other side as well. All right, let me go ahead and reestablish my equal sign. I'll go ahead and bring this stuff down. I get negative 1/6 e to the negative 2 theta cosine of 6 theta minus 1 over 18 e to the negative 2 theta sine of 6 theta. Over here, I have 1 integral, but then I have plus 1/9 of the same integral. So in my book, that makes 10/9 of that integral. Well, see, now I'm going to get my answer because I'm going to treat it sort of as like my unknown, well, it is an unknown quantity right now. But if I simply multiply both sides by 10/9, I will know what this answer is because there's no integrals over here. So multiply both sides by 10/9. Actually, 9/10, sorry. And multiply through, let me see, if I multiply through by 9/10, you know what, I might instead, I'll make this into a negative 3 over 18. I think it's going to be easier to do that way. The reason why I want to do that is because I'll take out a negative 1 over 18, I'll take out an e to the negative 2 theta. So if I took all that out, it would leave me with 3 cosine of 6 theta. And over here, I'll be left with plus sine of 6 theta. And now you can start to put your c because I've completely finished the integral. One last step is this little bit. And I end up with negative 1 over 20 e to the negative 2 theta. 3 cosine of 6 theta plus sine of 6 theta plus c. If I let this be u, the derivative is 1, but to take the integral of that, I don't even know where I'd begin. Even if it was just an x, I'm not sure how I would begin it. So, well, I would use integration by parts, actually. So what I'm going to do instead is I'm going to let this part be u. So I'm going to let u equal arctangent of x squared. That way the derivative of u equals 1 over 1 plus this quantity squared, and then take the derivative of what's inside. So that'll be 2x dx. And then my dv will be x dx. And it's very easy to integrate that. You get 1/2 x squared. So I'll end up with uv. I'll have 1/2 x squared arctangent of x squared. And you'll go ahead and put your limits of integration on that particular piece. And then I'll have minus v du So the 1/2 here will cancel with the 2 there, but I will end up having an x cubed. And I'll square the x squared to get that. Well, this is shaping up to be very nice, because now I can do a substitution here. Let w equal 1 plus x to the 4th. And dw will equal 4x cubed dx. I'll divide by the 4. And let me go ahead and get this part here. If you plug in 1 over radical 2 and square it, you'll get 1/2 arctangent of 1/2 minus, then if you plug in 0, that all goes away. Now over here, I'm going to have the minus 1/4. The integral now, since I'm changing it to w, if you plug in 0 for x, you'll get 1 for w. And if you plug in 1 over radical 2 for x, 1 over radical 2 to the 4th power is 1/4. You'll get 5/4. So I have a du, or dw, over w. That equals 1/4 arctangent of 1/2 minus 1/4 ln of w. And I'll put a plus c now. I didn't put absolute value around it because these are both positive numbers. 1/4 arctangent of 1/2 minus 1/4 natural log of 5/4. Now for the other part where you subtract off, or you, in this case, add 1/4, when you plug in 1 into ln, it'll be 0, so it goes away anyways. Reduction formulas. And the way these work is you start with an integral that may have certain powers or something like that, and try to whittle the powers down so that you can keep working the problem until you eventually get down in power to an integral that is very easily done. Let's start with my example and you'll see what I'm talking about. Suppose I want to do x to the n. I don't know the n. Sine of ax dx. And let's say we know this. N is, let's make it a natural number. And then a is just a real number. Just make sure it does not equal 0. That's the only thing that matters here. It won't let me do a lot that I want to do. So then probably the best uv that you can possibly do, if I pick my u to equal x to the n, du will have a lower power. In this sine, when you go from sine and you integrate it, you get cosine or negative cosine. It really doesn't matter, but you'll oscillate between sine and cosine forever if you allow that to be v. But this, if you keep allowing x to the n to be u, it'll keep going down in power. So let me show you what I'm talking about. U equals x to the n. Du equals nx to the n minus 1 dx. Then dv will equal sine of ax dx. And just as before, then v will equal 1 over a cosine of ax, and it'll be negative. So what does that do for me? The integral of x to the n sine of ax dx will equal, I'll do uv, so I'll have negative x to the n over a times cosine of ax minus v du. So here I'll get the minus and this minus will cancel. So I'll get n over a, and then I'll have the integral v would be cosine, so I'll have x to the n minus 1 cosine of ax dx. So you see that what I've accomplished is this. The power that's on x is now smaller. It's 1 smaller than it was before. Conceivably, I can run this thing again and then get an x to the n minus 2. Run it again, then you get an x to the n minus 3. Eventually, you're going to get down to no x and just have to integrate a cosine or a sine, which is really easy to do. This part right here, that's the reduction. Now, interestingly enough, I didn't do one for cosine, but I bet you could guess it. If I wanted to do x to the n cosine of ax, what do you think it would be? Use this as your guide here. Now, if sine had a cosine in it, and this negative probably came, where's this negative? From doing this piece. If cosine was in that place, it wouldn't have had a negative there. So I'll bet you it equals x to the n over a, and then right here, instead of a sine, you're going to, instead of cosine, you're going to have sine. And then here, it almost seems inevitable you're going to have a minus because that was a plus. And when you do the v du, that negative happened to cancel, but it's not going to if that negative is not there. So I'll have minus n over a, the integral, x to the n minus 1, and then this will have to be sine of ax dx. You can verify that with exactly the same steps that I used before. Let's put this thing to use. For my last example, x cubed sine of x dx. If you look at the formula, n then is 3. And then the a is the number in front of x. In this case, it's a 1. So let me use the formula for sine to write this part of it. Negative x to the third over 1 cosine of x. I'm not going to write that 1 anymore. Plus, well, I might here. N is 3, a is 1. 3 over 1, the integral. X, n minus 1 is then going to be 2. And then I'll have cosine of x dx. So I have negative x cubed cosine of x plus 3. Now what I'm going to do here is I'm going to use the reduction formula for cosine. You see, I was able to deduce cosine without actually doing anything, just realizing that it's kind of the opposite of sine and just switching their roles. That's all I did. It's recognizing a pattern. So now if I'm going to use this formula, my n is 2 and my a is also 1. So I'm going to have x squared over 1. So I'll have x squared over 1 sine of x. And then I'll have minus 2 over 1, the integral, x to the what now? X to the 1 sine of ax. Let me simplify. So I'll have negative x cubed cosine of x plus 3x squared sine of x. And then here, I'll then have minus 6 integral x sine of x. And I'm going to use the formula for sine one last time. This time, the n here is 1. That's 1. The a is also 1. So I'll get negative x cubed cosine of x plus 3x squared sine of x. I bet you could sort of tell what it's going to be. Without doing that stuff, I'll bet you, just looking at this pattern, 3x squared is the derivative of x cubed. So I'm wondering if my next one is going to be like a 6x. And then it's also going to be, here's my guess before I even do anything, minus 6x. And since it's going cosine, sine, it would have to go cosine next. And then for the very last one, it would have to go be positive. But then the derivative of 6x is just 6. So I have a plus 6, and then I'll have to have a sine of x plus c. Let me see if that actually does happen. Let's tuck that away for a minute. And instead, let me have this guy back. Okay, now then, let's take this part out. All right. Then x to the n is 1 and the a is 1. What we had for the sine one, then where to go for sine? Sine, then, if n is 1 and a is 1, we'd have negative x to the 1 over a, cosine of x, and then I would have, what was the next piece of it? Plus 1 over 1 integral x to the 0 and then that piece here, I'll get my sine had a negative there. Let me put that. That equals negative x cubed cosine of x plus 3x squared sine of x. Now I'm getting positive 6x cosine of x. Uh-oh, I feel nervous. Let's see what else goes on here. Then I'll have negative 6 integral to sine of x dx. And of course, this will end up being positive 6 cosine of x. And this last one then will be positive. I have a feeling that in my guess, the one that I was trying to guess the answer beforehand, that I must have, well, let's see. There's where my error is. And then I will get my minus 6 sine of x plus c. So what was my guess? I did not get this plus right, so let's go ahead and just mark it. But it was an attempt to see if I could spot a pattern that I thought was happening. The pattern is more complicated than what I initially gave it credit for, I guess.